Okay, we're going to be talking about continuity on an open interval. So we need to state this: a function f of x is continuous on an open interval ab if it is continuous at each point in the interval. If the function is continuous on the entire real number line, then we say that the function is continuous everywhere, or sometimes we say everywhere continuous. Alright, so get this down. Alright. This is something here that I just want to state real quick. I've mentioned it a bunch of times in some of the other videos, and discontinuities fall into two categories. They're either called removable or non-removable. Removable discontinuities is when you have a missing point in the graph, or you might have a missing point and it's actually defined somewhere else, like I've got stated here. Non-removable discontinuities are things like jumps in the graph and vertical asymptotes, which I don't have labeled. I don't have a vertical asymptote here, but you know what one looks like. Okay, so we have a polynomial function, and we're on the open interval between -2 and 2. So f of x is continuous as long as it's continuous at every point inside of this interval. Right, so f of x is continuous at every point in the interval between -2 and 2, but moreover, f of x is everywhere continuous. I think I stated it continuous everywhere last time, but I think this is the more proper way to say this, is everywhere continuous, and that means on the entire real number line. So if it's continuous on the entire real number line, then it's obviously going to be continuous in this interval. And of course, this is the graph. Think of it this way, right? If I'm got my pen on a piece of paper and I'm moving and I'm sketching this graph out and I'm moving my pen, if I don't lift my pen up at any point along this graph as I sketch the graph, then we could pretty much say that this graph is continuous. There was a theorem here that I'm going to go ahead and state. Kind of tells us about polynomial functions being continuous on the entire real number line, and that is the limit of a polynomial function. If h is a polynomial and c is a real number, then the limit of h of x as x approaches c is equal to h of c. And remember, this was the criteria here for a function at a point to be continuous. Okay, remember, this is one of the main properties. Okay, let's look at this function here, 1 over x squared. And where is this function not continuous? Well, it's not continuous at this x equals 0, right? Because we got a vertical asymptote. But actually, we are stating the domain here. We're defining it to be between 0 and 2. So it's continuous at every point between 0 and 2. Right, except at 0 and 2. Can't choose the endpoints. It's got to be everything inside of this interval. So let's say 2 is here. Alright, so this is going to be a continuous line. And of course, as x approaches 0, we go to infinity. Alright, let's look at this function here. We're in the interval between 0 and 4. Now, if it's continuous at every point between 0 and 4, then this function is continuous on this open interval. Okay, but what about a 2? If I plug 2 in, I get 0 on the bottom, get 0 on the top, and therefore you get 0 over 0, which means that there's a hole in the graph at 2. So that means that this function is not continuous at 2. Right, so since f of x is undefined at x equals 2, since f of x is undefined at x equals 2, then we conclude that f of x is discontinuous at x equals 2 and continuous at every other point in the interval 0 to 4. So as you can see, here's the graph, and this right here, this hole right here, indicates where it's discontinuous. Alright, let's state this definition. We got continuity on a closed interval this time. A function f is continuous on a closed interval ab if it is continuous on the open interval. And taking the limit of f of x, x approaches a from the right hand side, is equal to f of a, and the limit of f of x approaches b from the left-hand side. Okay, we got kind of abruptly cut off in that last part of that video, so I'm just going to kind of start over here. We're looking at the definition of continuity on a closed interval. A function f is continuous on the closed interval ab if it is continuous on the open interval ab, and, right, so this has to be true here, that the limit of f of x approaches a coming in from the right hand side is equal to f of a, and the limit of f of x as x approaches b coming in from the left hand side is equal to f of b. I've got some other stuff stated here. Let's see. The function f is called continuous from the right at a and continuous from the left at b. Okay, and I've got an example. Alright, here it is. So we got the function f of x equal to the square root of x, so I just picked something simple. Here's our closed interval between 0 and 6. So we want to first check the limit coming in from the right hand side. Right, this is our a here, coming in from the right, and then right here 6 we're coming in from the left hand side. Right, so that limit's got to exist and it's got to equal f of 6, and I got this worked out. Okay, so we're going to look at this one first. We're coming in from the right hand side of our function square root of x, so I just do the direct substitution, plugging 0 directly in, and we get 0 out. And then we need to actually check this, so we do f of 0 and we get 0, and therefore, right, these are both equal. So that's good so far. Now let's check coming in from the left hand side at 6. So what I'm going to do here is just do the direct substitution and plugging 6 directly in, and you get the square root of 6, and then we evaluate it, plugging 6 into the function, which sounds like the same thing I just did, but it's actually not. And we also get the square root of 6, and these are both equal here. So that's good so far. So remember that fits this part of this definition of continuity on a closed interval, right? So both these were equal, and both of these were equal right here. And our function is continuous on the open interval between a and b, and that was something that we talked about in the previous ones. Of course, we can just kind of tell by looking at the graph that the thing's continuous, right? Even though if we sometimes graph these functions and missing points, you can't actually see them on the graph because they're the size of a pixel, and that's pretty small. But anyway.